Ladies and gentlemen, good afternoon. My name is Zhu Yuhao. I'm from the China University of Geosciences, Beijing. I'm glad to have this opportunity to attend the conference and share our research with you. The topic of my speech is the field test of thermoelectric generators for recovering industrial waste heat. Firstly, I would like to introduce the motives of this study. According to a summary, there were few studies of TEG with a power output of more than 100 watts, and fewer studies with temperatures below 100 degrees Celsius. It is of great significance because there is huge waste heat within this temperature range. However, it is still a big question and a great challenge to use TEG devices for large-scale power generation with temperatures below 100 degrees Celsius. Thermoelectric modules could convert thermal energy directly into electricity based on the Seebeck effect. When there is a temperature difference between the two sides of the thermoelectric material, the movement of the carriers makes the thermoelectric module generate the Seebeck voltage. The expandability of a TEG device is very important to generate power at a large scale. The TEG we built is hierarchically expandable. It is easy to assemble and expand. The operation process of the TEG system is very stable. Even if there's a problem, it is easy to repair. These are the two TEGs we assembled in the field test. One 10-layer and one 20-layer. The 10-layer TEG has 24 modules per layer, and the 20-layer TEG has 18 modules per layer. In the picture on the right, we used the TEGs to illuminate the working area so that we could complete the test. We conducted the field test of TEG using the waste heat with a temperature of 80 degrees Celsius at a gas power plant located in China Shanxi province. The gas power plant has 3 gas generators. The waste heat mainly exists in the exhaust gas emissions and the engine cooling closed loop. To maintain the operating temperature of engines, the inlet temperature of coolant must be kept at 76 to 78 degrees Celsius, and the outlet temperature below 90 degrees Celsius. A large amount of waste heat was carried out by the coolant flowing in the closed loop. Especially in summer, the outlet temperature of coolant could reach 92 to 93 degrees Celsius, close to the shutdown temperature of 95 degrees Celsius. The coolant of engines was cooled by an external heat exchanger and then flowed back to the gas generators. The heat in the engine cooling closed loop was transferred to the heating network through the external heat exchanger for external use. The working fluid in the heating network was water. Considering the safety issues, and in order not to interfere with the operation of gas generators, we didn't choose to install the TEG to replace the external heat exchanger. The installation site of TEG was chosen in an area where the heating network passed through and near a water tank. The selected part of the pipelines was fitted with pressure gauges, temperature gauges, control valves, and multiple outlets. 2 flow meters were installed at the outlets of the hot and cold sides, respectively. An electronic load was used to provide an external load and measure the voltage, current, and power output. We studied the effect of 3 factors on power output and efficiency, including the temperature difference, and flow rate on hot and cold side. In the laboratory experiment, the power output of TEG was proportional to the temperature difference. In field tests, it is inconvenient to adjust the water temperature at will. The results measured at different temperatures were relatively few and did not vary much from each other. We quoted data from a geothermal field test we reported before. The power output increased with the temperature difference, and the power output from the field test were greater than those from the laboratory experiment, especially when the temperature difference is great. The difference in the fluid pressures caused the difference in the power output between the field test and the laboratory experiment. The pressure in industrial pipelines is often higher than the pump pressure in the laboratory. At higher fluid pressures, the thermoelectric modules installed between the fluid channels could have better contact with the fluid channel walls and less thermal resistance, which could improve the performance of TEG. The efficiency of TEG in the field test was similar to the laboratory result. The efficiency increased with temperature difference. The highest efficiency of the TEG devices in this field test was about 1.72% at a temperature difference of 60 degrees Celsius. It is interesting to observe that the efficiency of TEG fluctuates in a lower range, around 1%, until the temperature difference reaches 60 degrees Celsius. In contrast, the efficiency of TEG in the geothermal field test rose to more than 5% at a temperature difference of 152 degrees Celsius. The efficiency of the geothermal field test was variable among the tests at different flow rates. The results of the field tests and laboratory experiments suggested that the temperature difference of 60 degrees Celsius may be an important turning point for the efficiency of TEG in industrial applications. We changed the hot water flow rate. As the flow rate increased, the power output of the TEG increased, but the efficiency of the TEG decreased. There is a peak phase of efficiency at hot water flow rate between 2 to 3 cubic meters per hour. The power output had also increased to a higher range when hot water flow rate was between 2 and 3 cubic meters per hour. The hot water flow rate of 2 to 3 cubic meters per hour might be a reasonable range to achieve high power output and high efficiency of the TEG at the same time in these cases. When we change the flow rate of cold water, as the flow rate increased, both the power output and the efficiency of the TEG increased. When the hot water flow rate is constant, if we increased the cold water flow rate, the TEG could harvest more thermal energy from the hot water, so the efficiency increased. The TEG could have maximum efficiency at a cold water flow rate of about 3 cubic meters per hour in these cases. As discussed above, the proposed 10-layer and 20-layer TEG devices could achieve high power output and high efficiency at the same time when the flow rates of both hot and cold water were in the range of 2 to 3 cubic meters per hour. Based on the results of the field test, the installation cost and the levelized cost of electricity of TEG at different temperatures were calculated with reference to the cost data of geothermal power generation. The levelized cost of electricity of TEG could be comparable with the average cost of fossil fuels when the temperature difference reaches 150 degrees Celsius. As reported by Li et al., the cost of TEG is also attractive compared with PV panels if the capacity factor were considered. Compared to other renewable energy sources, the installation cost of TEG is advantageous when the temperature difference reaches 150 degrees Celsius. At a temperature difference of 60 degrees Celsius, our 20-layer TEG generated 167 watts of electricity. The power density was 4.66 kilowatts per cubic meter. This is a good result compared to some other high-temperature applications. It is obvious that the power density of TEG increased with the increase in temperature difference. Also, we noted that Li and Li reported a TEG with a very high power density, which would be more advantageous if their design could be scaled up. These are some of the findings based on this study. We assembled two TEGs and used them to recover waste heat at a temperature of 80 degrees Celsius. The efficiency of the 10 and 20-layer TEG devices may increase, stay constant, or even decrease with the increase in the flow rate, but there is an optimal flow rate range of 2 to 3 cubic meters per hour. The field test results were better than that in the laboratory experiments. The cost of the TEG devices decreased with the increase in the temperature difference. This work was financially supported by Huaying New Material Technology Group Corporation Limited. Their contributions are gratefully acknowledged. That's all for my presentation. If you have any questions, please feel free to contact Professor Kevin Li or me. Here are the email addresses. Thank you.